Well, hello. Apparently I'm live. Let's see. It looks like I'm live, yes. So hello everybody. This will be a weird stream for two reasons. First of all, there's nobody else in here. There's neither a flat earther nor any one of my colleagues. So you'll be stuck with me tonight. Second of all, I won't deal with a flat earther or a flat earther's video. I won't deal with any flat earther claims today. Instead, I will actually address something that I think at this point is quite necessary, namely the possibility on how to model things in two-dimensional programs. Now, in the past, mainly in the last week, we had some claims from the flat earthers that the Earth's radius would influence the obstruction height of an object in a way that it obviously doesn't. And unfortunately, I wasn't available really to intercept this or to deal with it and explain to them how this works. So I will show you today on how to use a program that allows you to do this. And if any flat earthers are in here, I strongly encourage you to listen to this so you can actually model shit yourself. Okay, so let's start. Let me share my screen. Okay, so the program I'm gonna use today is called GeoGebra. You can download it from this website here. And I strongly encourage you to use an older version, namely GeoGebra Classic 5. The reason is that even though Classic 6 has a little bit more functionality, the graphical user interface has changed and it sucks. The new one is it's just crap. The old one is much better. So if you're running Windows, just download it here. I think it directly gives you the exe file. If you're using Mac or Linux, well, screw you. No idea how to do this there. So that's pretty much it. Let's go right into the program. I already started it. In the beginning, I'll just show you some basic functionality. So you got your 2D plane over here, X and Y values. You can set points, lines, angles, circles, anything you want, basically. For example, so you have this input line you can use, in which you can, for example, directly enter functions. Y equals X, obviously you'll get a straight line with the slope of 1, or Y equals 1 divided by X, in which you will get this hyperbola, or something like, for example, X squared plus Y squared equals 25, in which case you will get a circle with a radius 5. So the line you get there is actually quite a powerful tool. The input line is actually the one I'll be using the most during this live stream. So something else we're gonna use are those sliders. You can place them anywhere, give them a name and a range. For example, from -10 to 10, 0.1. And those sliders, the output of those sliders, the value you set with those can actually be used for a function. For example, if I have the function y equals sinus x, you will get obviously this function. However, I can multiply this with the output value of the slider. And now, since I can change the output value of the slider, I can change the function on the fly. So I can use this to directly influence variables for the geometrical or analytical properties of this, whatever I'm doing. And obviously I can use as many as I want. So let's call this one slider 2. Let's give this the value from, -5 to 5 is fine. And if we're drawing a new function, for example, y equals slider 1 multiplied by sinus x minus slider 2, I will have the same function with the exception that I can phase shift this entire thing. So this is quite neat. Obviously, I can vary the rest. For example, the frequency of this function, I can turn it by an angle, anything. Okay, next thing, I can just define random points at any position that I want. which will become useful. For example, y equals, name of the point would be point equals, and then the x and y values. For example, 1 and 2. So I will get this point here at 1, 1, 2. So that this is pretty much everything that we are gonna need, with the exception of, obviously, we're gonna deal with some angles, we're gonna deal with distances. Yeah, that's pretty much it. So what I'm gonna do is, actually I'm gonna open a new one, because we're not gonna need this anymore. What we are going to do today is I will model the observation of Mount Rainier and Mount St. Helens, depending on whether you're on a flat surface or on a sphere. And obviously I'll parameterize everything, so you'll be able to set the observer height, the target distance, and the Earth's radius in case of a spherical Earth. So let's just start. Obviously we need a start point, so this is observer sea level, and I'll just define this as 0, 0. Okay. Now, to the scale, I'm gonna do everything in kilometers. So 1 unit to the right would be 1 kilometer of distance. So what do we have to start with? Obviously, we have to start with the observer height. I'm gonna use 3 sliders for this. So observer height in kilometers, obviously starting from 0 to, let's say, I don't know, 10, increment 1. I'm gonna use second one for observer height meters. Obviously in this case I need to set it from 1 to 1000. Oh, not 100, 1000. Increment of 1 as well. And the third one, observer height in millimeters. So I can set this pretty much with a sliding scale from 0 millimeters height, meaning your camera is directly on the floor or on sea level, to 10 point something kilometers. Okay, so now we have to find out where exactly our observer will be. So I'll set the sliders. So by the way, when you change your view, the sliders will stay at the same point, so we don't have to care about that. You can set it the way that they will move with the entire drawing, but I like to keep it this way because obviously I'm interested in watching the positions on what exactly happens at the targets, the angles when I'm changing this, so I'll keep it this way. Okay, so where's our observer? Our observer will be at a position of x equals 0, obviously. But what's our y value? Well, we've set the observer height in kilometers. Not this. There we go. So equals 0. Observer height kilometers plus 0.001 times observer height meters plus 0.000001 times observer height in millimeters. Okay, let's save this. Obviously we get our point observer, and now we can change his height in kilometers over here. We can change his height in meters. If I zoom, by the way, this obviously this live stream will involve a lot of zooming. In meters. So for example, right now it's set to 100 meters of height over sea level. And if I zoom in all the way, so from here to here, that's 1 meter. I can set it from 0 to 1 meter of height. I'm just gonna do for the rest of this, I'm just gonna set the observer height to 1 kilometer. Obviously, we'll be able to change that later. Okay, so we got our observer. Now it's time to get 2 targets, representing the 2 mountains in question. Okay, this will take a little bit more of zooming. Okay, so first of all, we need our target 1 base. And for this, we need more sliders. So, got target 1 in kilometers from 0 to, let's say, 200 increments of 1. And we need a second one for target 1 in meters. Yeah, from 0 to 1000 increments of 1. Obviously, we are not going to use millimeters. That would be overkill for this. Okay, so we got the those will be for the distances. What we're gonna need as well is for the height. So we need 2 more sliders, which would be target 2, target 1 height, kilometers, from 0 to, let's say, I don't know, 6, 1. And last but not least, target 1 height in meters from 0 to 1000 in increments of 1. Okay. By the way, everything I'm doing today will be uploaded to a Google Drive, so you can use it later if you want to. Okay. So, we're gonna need 2 points here, obviously. First of all, we're gonna need target 1, let's call it base. That will equal the distance in target 1 kilometers plus target 1 in meters. And on the y-axis, it will be 0. So let's see if this works. Yep, seems to be working. It's moving all the way to 200 kilometers if I wanted to, and in meters. Yeah, I'm an idiot, obviously. Because I need to delete this value by 1000. Let's see if this works. There we go, that's much better. Okay. And obviously, we will need, yeah, exactly. And obviously, we will need something for the top point of the first target. So target 1 top equals, now it's getting complicated, target 1 kilometers plus 0.001 times target 1 meters on the x value, and on the y value it will be target height, target 1 height kilometers plus 0.001 times target 1 height meters. There we go. So as you can see, when I set the target height for higher, for example, for 4 kilometers, this point will be moving vertically. Okay, so what are we gonna need now? We're gonna do the same thing again for the second target. But before we do this, let's just draw in some nice lines for the representation of the targets and the observer height. So you can just select a segment and then click 2 points to connect those. So let's call this target 1. And let's just change its color a little bit so I can see it better, and you maybe as well. I think you can make this a little thicker. And let's do this in, I don't know, some sort of gray. Okay. And obviously, I'll do the same for the observer. So let's make this also gray. There we go. shit. I don't know. This will do. Okay. Okay, what is the interesting thing about this? First of all, something I recommend doing is, obviously we want to draw a line from the observer to the target, top of the first target, to see how much of the second target is actually hidden. So this works the same way, only that we are gonna select the ray instead of a line or a segment, because extrapolating this line back into the negative values on this scale makes no sense. So this line now connects the observer position to the target top of the first target. So I'm gonna make this one in red so you can see it better. So this is line of sight target 1. And let's do this dotted. I hope you can see it. By the way, if there's something wrong with the audio setup, tell me. Okay, so let's test this. If I set, for example, the target distance or the target height, let's try this. The line is gonna change with it. Obviously, this I can do this in meters and in kilometers, the same way as before. So this works nicely. Okay. Alrighty then. Now we're gonna do the same thing for the second target. Ugh, I know it's hard work, so. Target 2 kilometers. Let's say again from 0 to 200 in increments of 1. Target 2 in meters from 0 to 1000 increments of 1. Target 2 height kilometers from 0 to, say, 12. And last but not least, target 2 height meters from 0 to 1000 in increments of 1. Okay, so those are all the sliders we will need for the second target. Okay, so we're gonna do this the same way as before. I'm just gonna set the target distance to, let's say, it's a bit low here, because I want not have to rescale everything all the time. Let's say 9 kilometers distance and height 2 kilometers. Okay, so the same way. Target to base equals target 2 kilometers plus 0.001 times target 2 meters. And on the y-axis it's 0. There we have our target 2 base. Okay. And then target 2 top equals target 2 kilometers plus target 2 that's the x value. Obviously the height value is target 2 height kilometers plus 0.001 times target 2 height meters. Okay. Now we got our target 2. Ain't it nice? The same thing again. So this is now our target 2. Color, I think was it this gray? Who gives a shit? Okay. And let's actually add another array from the observer to target to top. let's make this one green. So line of sight, target 2. And I think I made this one dotted as well. Yeah, there we go. Okay, now what we're interested in is when we change the target heights and distances, how much of the second target can you actually see, how much of it is blocked by the first target. So what we're actually interested in is the distance between this point and this point, because this is the line of sight projected on the second target, and obviously this point and this point. So this one here, this is the obstruction height on the flat Earth from the first target onto the second one, and this is the part of the second target you can actually see. So how do we do this? Simple. We can use this intersect tool and then select this line, the side line, and this one. We get this point as a result. Obviously, also independence of your observer height, for example, and all the other values that we just changed. As you can see, if I increase the observer height, we'll be able to look over target 1 and see more of target 2. Okay, so let's rename this point. So this will be... And by the way, you can also obviously do this with a command tool. I just think it's easier at this point to do it graphically. So this would be lowest visible on target 2. And what we need now is just to draw in a scale that shows us how much of this is hidden. So there is a distance tool somewhere. This one, distance or length. And we just plug in this value at this point and this point. It will give us the distance. In this case, it's 1 kilometer. Obviously, again, you can change this. For example, when we increase the observer height, we will be able to see more of the target. So now we would be at 1.5 kilometers. And obviously, this is also dependent on everything else. So, well, except for this, because the observer height and the target height are identical. For example, the target height in meters, target 1 height. If the first mountain is higher, we'll be able to see less of the second one, obviously. Okay, so this one is interesting. And the other one that interests us is actually the obstruction height. So this would be this value. Where can I move this? Oh, there we go. Okay, so what we got here now is actually a flat Earth prediction that tells us on how much we would be able to see of Mount Rainier when Mount St. Helens is in the front. Or was it the other way around? I think Rainier was the bigger one, wasn't it? So when we set the distances, and I challenge you to actually try this yourself, when we set the distances correctly, with the observer height, I think it was about 300 meters or something. Target 1 distance was 668, 86, something like that. I don't remember actually. And the target 2 distance, we will get 170 something. I don't remember. We will get a accurate representation of what we would expect on the flat Earth. So let me just save this. So this would be obstruction flat. Okay. So I think it would be boring you a little bit if I did the entire thing on the globe Earth, because I've actually prepared this before. So let me open this file, which is not complete yet. So we're gonna add, because I currently only have 1 target in there, so we're gonna add the second one. Where is it? Is it under models? Oh no, 2D representations. There we go. So the other one that I've used so far is called Horizon Drop Hidden Values. This one is quite interesting. It's pretty much the same thing that I've used, or that I've showed you before. The only difference is that it's working on a globe Earth. So I'm just gonna zoom out a little bit. You can set the Earth's radius. I've limited this to from 6,300 to 6,400, obviously. If you want to change that, just click on Object Properties, and you can set the minimum and maximum values here. I just said it this way because it's easier to fine-tune it a little bit. But if you want the Earth's radius to be, I don't know, 2,500 kilometers, you can set it here and then just slide it all the way back. Obviously, this will completely fuck up everything else, but it works. So let's go back to 6,300. Okay. What I've done here is, again, this will involve a lot of zooming. Okay, so to explain this to you, the red line in this drawing, that's actually your eye level. So this, the angle between the y-axis and the red line, that's 90 degrees all the time. The green line, now that's a tangent line that connects the observer with his apparent horizon. So when we zoom out, you will see that it will, at one point in the distance, touch the surface of the planet and then go away from it again. So this is touching it at one point, so this is a tangent line. Now the angle between the two I can actually show you. It's called horizon drop in this model. I've set the target height to 10 kilometers, for example. You will get a, well, 3.2 kilometers actually. Correct, so 0 to 200. So, for example, if you're pretty much directly 71, so this correctly. Don't use approximate values, use the right one. There we go. Hey, Richard. So, if the Earth's radius is 6,371 kilometers, you're 10 kilometers above the surface of the planet, then the horizon will be 3.208 degrees below your eye level. And if you do the maths on this, this is actually correct. So you can check it if you want. I urge you to do it if you want to, and it's just pretty much unnecessary, but if you want to, you can do it. Okay, so this is one point. Obviously, height kilometer, exactly. So this is, so those three values are setting the observer height again. And so this model is a little bit more crude. It's only set to kilometers. Well, obviously the target height in meters, that's fine. Target distance is in kilometers. So you can actually see that, for example, how much is hidden. Height kilometers, let's turn that one down a little bit. So this black line here, that's our target. Target distance is, let's reduce target distance. No, actually, target height, 0. So target, there we go. That's a much neater presentation. So for example, since the green line is your horizon line, you would be seeing that in this case, 243 meters of the target would be hidden at this distance. Do me a favor, plug that into the Earth curvature calculator. Target distance 104 kilometers, target height 1,300 meters. No, not target height. Observer height 183 meters. Actually, let's do this live. So this is Metabank curve calc. Okay. Obviously, I'll use this in metric. Distance in kilometers, 104. View height in meters, 183. And we get hidden value of 243.58 meters. So you see, obviously this is rounded to one digit less, but it's working with the set radius. And it yields the same result as the Earth curvature calculator. Okay. So what we're gonna do now is we're gonna, the same way as before, we're gonna add a second target that we can show, and we're gonna draw in the sight line towards the first target and determine how much of the second target is actually visible. So we're gonna need 2 more sliders. Obviously, nomenclature here is a little bit different. So this is target to distance. Let's do the same thing from 0 to 200. This is in kilometers. Increment 1. And what do we need as well? We need the target height. I'll do this in meters. So target height, target 2 height in meters. Let's go from 0 to 7,000. Increments of 1. This is accurate enough for this. Obviously, I need to reset this one as well. Okay, so how do we actually determine where exactly on this line it should be? So what we need is we need to determine the angle between the observer at sea level, the center of the planet, and the base of the second target. So we have this neat angle tool. We can set an angle with a given size. So how are we gonna do this? So, yeah, exactly. Select a point. So observer sea level, center of the planet, and what's the angle? Obviously, first of all, we need it to be set clockwise. What's the angle? Easy. 360 degrees multiplied by target 2 distance divided by radius. There's something missing. Do you notice it? Obviously, we're not dealing with the radius here, but we have to deal with the circumference, so we gotta multiply in here the factor 2 pi. Is this correct? 360? I think it is. This looks okay. So just to make sure, we're gonna set the target 1 distance at this target 2 distance. What the fuck? 1,000 kilometers. What the fuck did I do here? 200. There we go. Much better. So we're gonna see target 1 distance at 104 kilometers. Just to make sure that this is working, it should be at the same position as target 1. Oh, however, the new... Ah, yes, we still have to rename this. So this will be... What the fuck? Draw this? What did I do? Okay, whatever. So this is target 2. Okay. How do we determine... Actually, let me move this a little bit further. Oh, actually, let's do it the other way around. Just move that one out of the way. Okay. How do we determine where the top of the target is? Obviously, it's not this y value of this plus the y value of the height. Obviously, there's a tilt between the two. So the way we're gonna do this is we're gonna draw another ray from the center of the planet to target 2. And now, first of all, we're gonna rename this somehow. I think it has, no, it has no name, so let's keep it this way. Okay. And now we're gonna draw a circumference with a given radius around this target. So what's the radius of this? Obviously, it's the target height. Actually, it's the target height in meters, so we're gonna multiply this value by 0.0001 times target 2 height meters. And we're gonna get this. So when it's set to 7,000 meters, obviously the distance between here, 102, and here, 95, yeah, that's approximately 7,000. So this one is fitting perfectly. And this is actually the reason why there was a circle on the around the other target as well. Okay. So obviously then this is our target top. So we're gonna need a new intersect point. Obviously we're not gonna need the one down here, so we're just gonna remove it, or well, it's still there, but we're not showing it. And then we're gonna rename this one to, what's the other one called? Target top. So this is target 2 top. Okay, so we're gonna remove, not this one as well. It's just unnecessary to show it. And we're gonna draw in another not an array, but a segment, which will be our target 2. I don't know how to name the first one, but whatever. So gray, make this a little bit more thick. There we go. Okay, now let me actually disable those circles, because those at this point are unnecessary as well. So how's that one called? D. Let's remove the D. Yeah, I know, enough of that joke. Okay, so how do we determine now how much of target 2 is hidden because of target 1? Well, the same way as before. We select our ray from observer to target 1 top. And let's go over here. Come on. Yes, we see how... no, this is target 1. Exactly. We see that everything below this point is actually hidden. So what's interesting for us, in this case, only how much of this is visible, because we don't care what's underneath here, because actually we can subtract the two. Plus, this is obviously dependent on whether the horizon is below the sideline to the first target top or not. So, and I actually got a Skype message, so let's see. Okay. Oof. So again, intersect from here to here. So the only thing we need is the distance between those two. So I'm gonna rename this to, how did I call it in the first one? Lowest visible on target, okay. Okay. And the last remaining thing to do is to check the distance from here to here. And that should be it. So let's try this out. Can somebody in the side chat please do me a favor and give me the data for the Mount St. Helens / Rainier observations? I think that... Oh fuck, I really don't remember. Height was somewhere between 200 and 350, so 250 to 350. And the distances... No one? Yeah, okay, whatever. I'll just set this something. So I think the first one was like 80 and the other one was like 160 kilometers away. Heck, I really should have written down those numbers. But as you can see, target first height was like 2.5 kilometers. Let's look this up. So, Mount St. Helens. That one is 2,500 239 meters. $2,539. Okay, that's 1 meter off. I guess that's justifiable. And Mount Rainier. That one is 4,392. Okay, so the only thing I need is the exact distances. If I get those, I'll be able to predict it. Well, obviously we can see here that if the numbers are correct, then Mount St. Helens is actually higher than Mount Rainier as seen from the position. Which is something, if I remember correctly, we don't expect from the Flat Earth model, do we? Oh, before I forget, I should save this. So horizon drop hidden values -2. Okay. That's pretty much it. Yeah, I know, Fino. Rainier's the far one, St. Helens is the one in between. That's correct. That's what I said. St. Helens at 2.5 kilometers and Rainier at 4.4. So that should be okay. And I urge you to compare this to the observation that was actually done. Now you know how to parameterize, you know how to change everything. I will upload all the files that I got on Google Drive. And obviously, if you have me in your Discord server list or something, you can just ask me. I'm going to send them to you. Do you have any questions? No questions? Okay, so since I think I pretty much have explained everything that you need to model this, I can I know what I'm gonna do. One more model that I've made is, I've actually showed this before in the hangout that I had last week with Shinobi, is a scale model of the Sun-Earth-Moon system. Same system. You can model this as well, obviously. In this case, we had the suns all the way to the left. I'm gonna show this to you. Yeah, why the fuck not? Again, lots of zooming. So sun's over here. In this case, I haven't set the sun diameter as a parameter, so this one is fixed. I could remake it depending on the sun's radius, but yeah, why should I? If it's necessary, obviously I can do so. Same for the Earth's radius in this case and the Moon's radius. But what I've been able to set is, I can actually show you that the Moon's orbit, obviously you know that it has certain eccentricities, so you can change the distance between the Moon and the Earth by the 45,000 or so kilometers. And obviously the Earth's orbit is also dependent on where exactly in its orbit it is. It's also an ellipse, so we can set the Earth's orbit a little bit further out or closer to the sun. And the interesting thing is what exactly does this do with solar eclipses? So those 4 rays here, those represent the relevant rays coming from the sun. And those 2 in the middle, those are actually determining the position and the size of the umbra. So between those 2 lines, the umbra of the eclipse is observed. And when you see that when we get the Moon closer to the Earth, obviously the point where the umbra and the end umbra meet will be further away. So in this case, for example, you would get a total eclipse, while here you would get an annual eclipse. Same thing. Just wanted to show that off. And with that, I think I'm finished for today. So thank you very much for watching. If you have any questions about the program, just ask me. If you don't, then don't. And to any flat earthers, I challenge you to actually try this, or at least to download my piece of software and actually try to model the distances. As you saw, it was directly compatible with the Metabunk calculator. It gave the same results. So we know that it works. And with that, I'm heading out. So thank you everybody for watching, and see you next time. Have a nice New Year's Eve. Tomorrow's the 31st, I think. Yep. So good luck in 2019. And I hope you had a nice 2018 and a nice Christmas.